Welcome back, students. In this video, we are going to build on what you have learned so far. We have come across Faraday's law and also Lenz's law. And now that we know these two laws, we will derive an expression for motional EMF. First of all, how is an EMF induced in an electric circuit? If the magnetic flux through the circuit changes, then an EMF will be induced in the circuit. That is Faraday's law. And how can the flux through a circuit change? It can change in one of the two ways. The first way is there is relative motion between the circuit and a magnet. If the magnet has fixed strength, then if you move the magnet towards the circuit, then an EMF will be generated. Or if you move the circuit towards the magnet, an EMF will be generated. If there is a relative motion between the magnet and the circuit, then you will change the magnetic flux going through the circuit. And if the magnetic flux going through the circuit changes, then an EMF will be generated. So the condition is the magnetic flux through the circuit must change. And how you change is the second part. So when you move either a magnet or a coil or both towards each other or away from each other, then you are going to get an EMF. So that is what we call as motional EMF. And what is the other type of inducing an EMF? Well, you have a magnet, maybe in this case an electromagnet, which means that you have a coil and it has a current flowing through it, a steady current flowing through it. So that coil will produce a magnetic field. Now you bring another coil. And if you change the current flowing through this coil, then the magnetic field of that coil will change. If the magnetic field of that coil changes, then the magnetic flux through this coil will change and it will induce an EMF. In this case, you don't have to move the magnet and the coil. They can be stationary. But then you are controlling the magnetic field by changing the current in the coil that produces a magnetic field. So the other coil will have an induced EMF. So that's the second way of doing it. But what we are going to do here is deriving an expression for motional EMF when there is a relative motion between the field and the circuit. When the flux through the coil is changed through movement. And that is what we are going to do now. So to do it, I am going to assume a few things. First, I am going to assume a magnetic field that goes into the board. And I will also assume that the magnetic field is constant. It's a permanent magnet and it is fixed, so nothing is happening to that magnet. So the field at any point is constant. So let's say this is the field. If you take this plane, on the plane, the field is constant. Okay. So this is B. Magnetic field lines are going into the board. And I am going to assume two rails, metal conducting rails, okay, like this. And they are connected by another conductor like this. So the length of this is L. The distance between the two rails is L. You can say that. So you connected this. Now it forms a U-shaped conductor. And on top of these rails, I am going to have another conductor, a rod, a metal rod. But then it's a sliding rod. Okay, so this is the rod. Now you can see that it forms a loop. It forms a circuit. So this is a conductor, this is a conductor, this is a conductor, and that's also a conductor. Now it forms a rectangular circuit. And since this rod can slide on these rails, I'm going to move this rod towards this part into the field, so with the velocity v. Okay. I can even name the ends of this loop. I'll call this as P, and I'll call this as Q, and I'll call this as R. I'll also call this as S. Okay. So this length I said is L. L is this length. So this length is L. Okay. And this length at any point in time is X, because it is changing. This length from here, if this is the origin, then that length is going to be changing. But this won't change, and B also will not change. I can move this towards this, or I can take it away from this segment. So this is a setup. Let's say I'm going to move this from here towards the magnetic field. Okay. Suppose it's here. Would you have generated an EMF when you brought it from here to from this position to this position? No. Why? Look at the loop. In this loop, these are the magnetic field lines. This is the flux. That's all I have here. Okay? As I brought it from here to this position, as the flux in the loop changed? No. I still have the same amount of flux. The flux has not changed. So no EMF would have been induced. As I brought it from here to here. And then I bring it here. Again, would an EMF have been generated? No. Why? The flux still remains the same. So no EMF would have been induced up till it reaches here. But once it gets into the magnetic field and as it comes towards the segment RS, you notice now from here, from this point onwards, okay, from this position onwards, as you bring it here, then the flux in the circuit changes. From then on, you can expect an EMF to be induced. Not up till here. As I bring it from here to this position, no EMF will be generated. Why? Because no flux is changing. But from this position onwards, if I bring the rod towards the segment and into the magnetic field, notice that the flux is reducing, changing now. If it is here now, suppose it's here. So clearly, the flux now has changed from this position to this position. So now you will have an EMF induced. And the EMF will keep getting induced up till you go here. And then suppose, and after that, you may take it in the other direction. We'll talk about that later. But understand that if it is here, no EMF is induced. If it is here, as I bring it from here to this position, no EMF will be induced because I am not changing the magnetic flux through this loop. But from this point forward, as I bring this rod closer to this segment, then I am reducing the flux in the loop. And if the flux reduces in the loop, then an EMF, there's a change in flux in the loop, in the circuit. So an EMF will be generated. Okay. Now, what is the flux at any point in time? Okay, flux phi V can be given. I'll start from this point. Okay, let me ignore all these positions. Suppose I start from here. So this is where I'm going to start. Okay, there my flux is actually equal to B into A. So what is that A? The A is going to be equal to B L, and if it is here at any point, at any x from the origin, and that's the area. So the flux is B into this area. Then you have one x here. So when if it is here, it is B L into this x. So x will be changing. B and L will remain the same. So based on the value of x, the magnetic flux through that will change from here to this position. Beyond that, that will remain constant. Whatever you had up till here will remain constant even if x increases. But we are bothered only up till here because we are interested in finding the EMF when it is induced. The EMF will be induced only in this region, not when it goes out. Okay, so this is our range. Okay. So to make it better, I can even reduce this. Okay, I just say this is it. This is my x, and this value is the maximum x, and this value will remain even if x changes. And after that, it won't change. But up till here, this will be changing. So B L x, that's the flux. Then what's the rate of change of flux? D phi by dt. So D phi d by dt, and that is equal to B is a constant, told you. L is also a constant, it's not going to change. But then you will have dx by dt because x is changing. But what is dx by dt? Dx by dt would be the speed, the velocity with which you are, the speed with which you are bringing the rod towards this. So that would be B L into V. But think about it. Is this a positive quantity or a negative quantity? It will be a negative quantity. The reason being, if you take this is my origin, let's suppose I am here, it's maybe 10 meters. So my initial position is 10 meters. And as I move to maybe this position, which is 9 meters, my initial is 10, my final is 9. Maybe I have taken 1 second to make this transition from this position to this position. So my initial is 10, my final is 9. So my delta x will be 9 minus 10 minus 1. And I would have taken 1 second to do that. So minus 1 divided by 1. So I get a negative number, minus 1 here, an example that we have taken. So V will be a negative number because you see you are reducing it, coming closer. So this would be negative number, minus BL. That's my d phi by dt. And what's my EMF? EMF generated is given by this expression. This is minus d phi b by dt, and that would be minus of minus BLB. So you are going to get a positive number. BL. So this is expression for the induced EMF. So this EMF will be induced in this loop as it goes from here towards this. Okay, now what is the direct direction of the current? What's the direction of the current in this loop? To find the direction of the current, I told you that you should be using Lenz's law. Okay. So what's the first step? We need to find the direction of this magnetic field. Okay. I'm going to apply Lenz's law. This is Faraday's. I'm going to do Lenz. Okay. First step. What is the direction of the magnetic field? Inside. Okay. Then, what is happening to the magnetic field? As I bring this rod closer and closer to this segment, the magnetic field through the circuit is reducing, it is decreasing. Okay. So, the second thing is, this X is decreasing. This is decreasing. So what should the induced EMF do? The induced EMF will tend to produce a current that will oppose this change. What is a change? Decrement. That is a change. So what should it do? It should oppose the decrement. Then what should happen? If this flux is reducing, the flux that is going into the board is reducing, then you have to increase it. Then how will you increase it? You will put the flux in the same direction. Then you will increase it. So, this current which is flowing in the circuit must send flux in this direction. So, if the flux has to go in this direction, then what should be the direction of the current? It is like this. So, the current will flow like this. So, this is the direction of the current in the circuit. It's a closed loop anyway, so there will be a current. If it is an open loop, there wouldn't be. Since it is a closed loop, then this is the direction of the current. So, what's the direction of the current? The current direction is I is clockwise. In your textbook, the direction of the current is given wrongly. So when you study this in your textbook, just keep in mind that the direction in your textbook is wrong. You have to use this direction. Just keep that in mind. Now what will happen if this rod is taken away? Well, let's say the rod comes and joins here, this segment. So the area is 0. There is L, but X is 0. But as you move this rod away, you notice that you are increasing the area, which means you are increasing the magnetic flux through the circuit. The magnetic flux is increasing. So in that case, what should happen? In that case, the induced EMF, clearly EMF will be induced because there is a change in flux in the circuit as you take it away. So it will produce it will induce an EMF, and that EMF will tend to produce a current that will oppose this change. What is the change? As you go from here towards that side, the change is that the flux is increasing. So the current that flows in the circuit must oppose that increment. So in that case, the current must put the field lines in this direction, because these field lines are going into the board, so the current must put field lines in the opposite direction. So then they will reduce. Because there is an increment, you have to reduce it, then you have to decrease it. So the current field lines will be in this direction. So the current will be in this direction. So in that case, the current will be in the opposite direction. That will be anti-clockwise direction. When you take this away, when you bring it towards RS, this will hold good. E is VLV and I is clockwise. When you take it away from RS, then current will be in the anti-clockwise direction. But what about EMF? EMF will be negative, obviously. Because if you have one polarity for this and you should have the opposite polarity for the other effect. And that can also be deduced from this. Why? Because notice now that you have x here, x could be small, initial x is small, the final x is big. So final could be 10 and initial could be 9 or 8. Because you are going away, so the x is increasing in this direction as you move away. So then delta x will be a positive quantity, so this will be positive, but then this will be negative. So the magnitude would remain the same, alright, but then you see the polarity would be different. Hope this is clear to you. The same result can be obtained by using Lorentz Force equation. You remember, which we studied in lesson 4. Actually, like Lorentz Force and Faraday's law are not different. They're pretty much the same. Like you can explain Faraday's law from the perspective of Lorentz Force too. Let's think about it now. Okay, what does Lorentz Force say? If there is a charge that is moving in the magnetic field with a velocity v, then the force experienced by the charge is given by F is equal to QV cross B. So that is Lorentz force. Let's see what happens here. Okay. No charge is right now moving in any of these parts. There is no net flow of charges, right? Kind of stationary. There will be a random motion of electrons inside, but then on the average it becomes 0. So I'm not even going to consider that. I'll consider that. I'll take it that there is no charge moving in this to start with. Now what I'm going to do? I have this rod and I'm going to move this rod in this direction. So if we move this rod from here onwards, as I move the rod towards RS, now I have brought the rod into the magnetic field. But then what does the rod have? It's a metal rod. It has protons, it has electrons, and then they are all tied together. They can't move all that freely, except the free electrons. The free electrons can move because they are not bound to any particular atom, so they can move. But the protons and electrons cannot move freely. Even though they experience a force, then they can't move all that freely. But the free electrons can move freely, and that is why they are called as free electrons. They are not attached to any particular atom. Okay? So as I move this rod from this position into the field, now all the charges are moving in this direction, including the free electrons, including the protons and bound electrons. All of them are moving in this direction. So all of them will experience a force. But the nucleus and the bound electrons cannot move away because they kind of they're held by the interaction of other forces. They can't move. But what are free to move? Only the free electrons in the rod are free to move. I have brought the rod here. Now the rod is moving inside. Nothing else will move except the free electrons. When they experience a force, all the protons and electrons will experience a force, but the nucleus and the bound electrons will not move, even though they experience a force, because they are counterbalanced by other internal forces. But the free electrons, they experience a force and now they are free to move. They are not bound anyway. So now they can move. And in which direction will they move? First of all, in which direction will they experience a force? Okay, this is the rod, and the rod is moving in this direction, which means that all the charges are moving in that direction first. Okay, so the free electrons are also moving in this direction. In which direction will the electrons experience a force? Let's see. If it's a positive charge, then it is given by this expression, right? The force experienced is given by Q V cross B. Okay. So now, as I move the rod in this direction, this is the direction of the free electrons. They are negative. Okay, we'll come to that later. So this is V. This is B. B is into the board. V cross B. So down. V cross B is down. But electron is a negative charge. So the net force is up. In the opposite direction. So the electrons in this rod will experience a force in the opposite direction. The free electrons. They are free to move. So all the electrons will go this way. They will start from here, they will go here, and then they will, because you have a path available, then they are experiencing force and you will flow through this. And as they come here, then you will take them out again, because the force will act in the rod, because that is what is moving. Nowhere else the conductor is moving, but only here the conductor is moving. So that is wherever the conductor is, this rod is there. The charges will experience a force in the rod, and the electrons, the free electrons, will experience an upward force. Using this equation, you can figure that out easily. So electrons will start from here, and they will go up, and they will go like this. Well, if electrons travel like that, then the current direction must be this. That is what is happening. So you can explain Faraday's law from the viewpoint of Lorentz force. It's like Faraday said, if the flux changes, then there is an EMF induced. Why? He doesn't explain it. But now you can see. Because the moving charge in the magnetic field experiences a force, when you have this kind of a setup, then you get this effect, the same effect, using Lorentz force. You can explain that. You can explain what happens or why it happens using Lorentz force. Okay. So hope this is clear to you. And this is the force experienced. And let me go ahead with it. Okay, so the force experienced by this is given by QVB. Okay. And what is EMF? EMF is voltage, I told you, potential difference. It's potential difference in this case it's going to be equal to E, which is electric field, and dot product of that and L. Okay, the length, work done. EMF is work done per unit charge. So the E into L. So that is going to be given by E is what? F by Q will give you. So you get V, B, and then work done is what? Potential, right? Potential energy. What is potential? What is voltage? Potential energy per unit charge. So VB into L. You see, you get the same expression here. So this is a work done. Okay, work done per unit charge. That's your EMF. That's potential, clearly. So you get potential energy, and then potential energy per unit charge is potential. So that's EMF. So you find the force, and from the force you can find E, which is force per charge will be VB, and if you and the work done is the force is acting in this direction, so it's going to take it from here to there. So this length is the distance over which the force is acting. So F into M. So just dot product. Okay. So and E direction and then L direction same. So you get cos theta will be positive. So let us make cos theta will be 1. So this will be VB. So you get the same expression here. So this is Faraday's view of what's happening, and this is Lorentz's view of what's happening, and they both mean the same thing. Hope this is clear to you. So now that we have derived the expression for emotional electromotive force, we'll do example 6.6, which is a slight improvement over that derivation. We're going to make use of the derivation to do this problem, but it is not a very simple problem in the sense it has some complexity involved in it. Let me read the problem. A metallic rod of 1 meter length is rotated with a frequency of 15 revolutions per second, with one end hinged at the center and the other end at the circumference of a circular metallic ring of radius 1 meter, about an axis passing through the center and perpendicular to the plane of the ring. A constant and uniform magnetic field of 1 Tesla parallel to the axis is present everywhere. What is the EMF between the center and the metallic ring? So the setup is like this. So they have a magnetic field. Okay, and in that magnetic field is a metallic ring. This will have some radius r, and from the center you have a rod that is touching this metallic ring, and it can move freely around it. So now the question is, this rod is moving around this ring like this, from the center. It's touching the ring and then it's moving like that. And what is the EMF induced in this? First of all, we need to understand that this would be one end. Okay? The rod is what is moving. So this will be one point, and then the other point is this, the other end is this, and all of this will be at the same potential as this end of the rod. So this is one end and that is the other end. So only the rod is moving, the ring is not moving, nor the magnetic field is moving. So the ring is stationary, so the ring will not have any effect on the induced EMF. What will have the effect is this rod. The rod will be going around like this, and if it is rotating like this, let's say with an omega, okay, it will have an angular speed of omega, and let's say this is r. Let me derive an expression first, and after that we can plug in the values. Okay, so what do we know first? Okay, if I have a small piece of the rod, I'll call this as, okay, this is r and this is going to be dr. Okay, so dr. If we take a very small piece of the rod, and as it rotates, it will move like this. The velocity of that would be in this direction. So the field is going in, and then the velocity of the rod is in this direction. So clearly, the electrons will try to move in the direction, because you're moving everything in this direction, right? So I'm using the Lorentz Force model to do this. This problem can be done in two ways. The first way is what I am going to use now. That is method 1. One is the Lorentz Force method. Okay, so in this method you can see I can take this as a small piece of that rod, and you know, it's moving with some velocity here, v, and if it moves with that velocity, then we know that the EMF induced in that small piece is going to be the small EMF. So I call this as dE. Small is going to be equal to. So what did we derive? We said it's going to be BLV, right? In this case, this is going to be B is the magnetic field, and then instead of L, you are going to have this, the length of this small piece, that's going to be dr, and then V. So that is the speed of this particular piece. So this is what you will use to get the EMF induced by this. Okay, let me take that rod. Take this rod. What you have done is for one small piece here. Okay, so this is what I call this dr, and if this is the origin, I will call this as r, and then as like you will have many drs like that, many drs like that. Okay, and each dr, because it is moving in the magnetic field, this will produce an EMF, and this will produce an EMF, this will produce an EMF, this will produce an EMF. So you can see that all the EMFs will get added. Okay, so if you want to find the EMF, which is the potential difference between this point and this point, then I have to be adding all these small EMFs that it produces. And the way to do it would be integral calculus. So the EMF induced can be written as integral of all the small EMFs in those small lengths. Okay, and that is equal to integral B, then dr, and then V. But what about V? B is a constant. Okay, B is a constant. But what about V? See, V is going to be different for different elements. So why? Because if I have a rod which is making a circle, then clearly this part will hardly move, and this end will have a maximum speed, and all the other things will have varying speed. So like from this part will have the maximum linear speed, and this will have less than that, less than that, less than that, less than that. So finally this part would not even move. So that we know from our circular motion. So your linear speeds and velocities will be different at different lengths, actually, from if it is at different distances from the origin, from the center. This will have one speed, this will have another speed, but all of them will have the same angular speed. So the angular velocity omega would be the same for all the pieces, but then their linear velocities will be different. So this will have something, and this will have something else, and this will have something else. Speed will be higher, like this. All of these will have different speeds, but even though they will all have the same angular velocity. So in that case, how do you represent each velocity? If I take a particular dr, small length here, and at this distance from the center, the distance can be considered to be r, and the velocity is, you know that it's going to be r omega for this. And as r increases, the velocity will keep increasing because omega is constant, but r, depending on r, depending on how far they are from the center, each small length will have different velocities, and that is going to be decided by this r, how far that piece is from the center. So there's a small piece that is a distance r from the center. That's what we're considering now. So this will have velocity r into omega. If I have something else there, somewhere else, then that distance into omega will give the velocity of that piece. So each piece will have its own velocity. That's the point I'm trying to derive it. So I'll get B, and then instead of V, I'll say r omega, and then dr. And where will it start and where will it end? It will start from 0, from the very center, and the r will vary from 0 to the radius of this. So if I integrate this, then what we would, B is a constant, B, and omega is also a constant, angular velocity is also a constant, and r into dr, so that will be r squared by 2. And if I were to apply the limits 0 to r, then I am going to have E is equal to B omega r squared by 2. And if you put r value 0, the next part will be 0. So this would be the expression for this one. That's the EMF between this point and this point. I've used the Lorentz Force method to do that. And they've given you different values for this. They've given you B value, they've given you omega value, they've given you R value. And if you substitute the values given in the problem, then you would get 157 volts. That's the answer. 157 volts. So this is the answer for this. If you substitute the values there. Hope this is clear to you. And the other method is Faraday's law method. So method 2 is Faraday's law method. Okay, so in this case, again, the potential difference would be between this point and this point. Okay, and then no current will flow through this loop. Notice, because all the points in that loop will be the same potential. So just because you have a ring doesn't mean that you will have current flowing through that loop. That wouldn't happen. Because notice here, this point is the same potential as everything else, and there is no EMF generated in this loop. EMF is generated only here. Why? Because that is what is moving. The ring isn't moving. So no EMF will be generated like that. Okay, so let's see. Next one, Faraday's method. So for this, what I'm going to do is, this is the point and this is this is starting point, and between these 2 points, O and let's say this is A. O and A, you will have the potential. What I'm going to do now is I'm going to imagine a circuit, okay? Because you know this, right? So there is a circuit, let's say. I'm going to have something like this. Okay, so I'm going to complete it. So this will produce the EMF, and that will send the current through this resistor. Okay, I'll call this as say 5 ohm or something. So now which is the circuit? This is the circuit. This imaginary thing is the circuit. And you can see that there is flux through this. So there is flux here, right? There is flux here. If this is a starting point, there is flux here. Magnetic flux is here. Until here there is flux in the circuit. But what happens here? This is changing. What is changing? This rod is going to move from this point to this point. Okay. If it moves to that point, you notice, and what is the circuit now? From here to here, and supposing that you are not doing anything else, if these 2 points are the same, so you see now the the circuit is something like this. Okay, like this. From here, from this shape, it has become this shape. So notice that within the circuit, the flux has changed. The circuit only had so much flux. Now, because it has gone from here to this place, it's from A to B. So you see, the flux in the circuit now is more. So the flux is changing. So how much is the flux changing? That's what we need to see. What is the change in flux? The change in flux is this. Suppose if this is the angle theta, let's say it has gone from this, from A to, okay, let's say this is theta, it has gone there. So you have added this flux, so that is a change in flux, right? So what is the change in flux now? The change in flux is going to be equal to this area, right? The flux in this area, that is the extra flux. So my delta phi B is equal to, suppose how much should the flux be there? Let me first find out the total amount of flux in the circle, and then I will take only this part of the flux. That's the change, right? So what's the total amount of flux in the circle? So the circle, in the entire circle, the flux will be B into area of the circle, which is pi into r squared. It's a total amount of flux. But now you got only one segment, right? So that is a change. From here, that is a change. So what is that area? And that area would be so from a geometry we can do that. That area would be this area is equal to, if this is theta, then this area would be theta by 2 pi into pi r squared multiplied by b, that's the flux now. So this is the area here, and that is what you get now. So then pi and pi will cancel. Then the change in flux from here to here, the change in flux is actually b r squared theta by 2. But now I need to do d phi by dt. So d phi b by dt is going to be equal to this delta phi by delta t. If I do that, then I get b r squared by 2 into this theta by the time it took to move. So that is going to be actually d theta by dt is what you get now. So that would be b r squared omega by 2. So you get the same answer. See. Again, if you substitute all those values, then you will get 157 volts there. Okay, all the values in the textbook, given the textbook. So you can do this problem two ways. You can take the Lorentz Force method and then consider only this rod and use it like this. You use the Lorentz Force method to find the equation, or you can use Faraday's law method and then come up with this one. So either way it works. So what we have done now is we took the basic equation of a motional EMF, and then we are applying it in a slightly more complex situation to find the EMF. Hope this is clear to you.